Zhang from Fudan University, and the height is smooth. Sorry, without maximal entropy measure in smooth surface system, and this is a joint work with Wang, which is joining our group. Do you know when he's coming? Because I know he has some problems with the visa.
Yeah. Because now he's trying to apply the visa with alternative offer. So I don't know his work, but anyway, he's already several before I called him. He said he needs some meeting. Yeah, but I don't know before
his way.
Yeah. Okay, for the morning, so thank the Professor Fitch and also thank Professor Gutman for inviting me here to give a talk about my recent results, and also thank Andan for arranging such a seminar for me. So the title of the talk was smooth curve without maximal entropy measure in smooth dynamic surface system. So this is good work with my student Wang. So this is today's framework. Today's outline of this talk. So today's framework is working in topological dynamic systems. So that means here T is a continuous set map over compact matrix space. And when we know the MX and MXT, so the state of all probability measures and the invariant elements of the space. In fact, in today's talk, we are more interested in the formula. That means the probability measure need not to be invariant. We will see. So we will know that in the study of topological dynamic systems, entropy is one of the most important concepts to reflect the topological system. We know it can measure the rate of increase of the orbit in dynamic system. And also, we know that there's a classical variational principle related entropy. So this gives a bridge between topological dynamic system and the algorithmic theory. So entropy will then play an important role in the study of the interplay between these two dynamic branches. So in fact, around 44 years before, the Professor Brin and Katok introduced the assumption of the local entropy in the measure-theoretic settings. This is their definition. In fact, given a probability measure, so the measure is not necessarily invariant. They can introduce some kind of the local entity for the measure. That means given a point x and given a parameter epsilon. So here we use this notation. So that means this is the nth moving forward. That means we can given a dynamic system, we can introduce a new matrix for all the systems, and then we consider the open form with the center x and the radius epsilon. So it's very easy to split. This function is measurable, so we can consider such two functions, and then we can reduce this function. So this is the local measure entropy used by Brin and Katok. And we consider that these two functions are measurable. So and then 31 years later, so Brin and Huang introduced the measure-theoretic lower and upper entropy just to take the integer of these two functions, because these two functions are measurable. So the interesting thing is this. They can do this through the following variation principle. So that means there are people are interested in the relationship between the measure entity and the topological entity. So they found they also have such variation principle. In fact, they consider the so-called analytic subset. So then they could prove that there is a variation principle between the lower measure-theoretic entity and the so-called forward topological entity. And also there's a similar variation principle for upper measure-theoretic entropy of we consider the measures support on this analytic state. So here is the depending on respectively the forward topological entropy and the pattern topological entropy. I will give each later in more details. So the analytical impact of state, the Polish mathematician made a contribution to this important state. That means analysis is a convenient means of Polish space. So it has made a good property. The most important thing for us today is that any analytic state is universal variable. That means for any given probability, for probability measure of the space, this state is also measurable in its condition. I mean, given a mu, then consider the condition mu, then analysis is in the mu condition for us as well. So we know that we know that the identity of these two identities in fact generalize the classical variational principle. So because where it's easy to say both these two are equal to the topological entropy of when we consider the whole dynamic systems, and also by the in the notation of Feng and Huang, and by the result of the famous result by Brin and Katok, we know that this lower entropy, this upper entropy, is in fact the usual measure-theoretic entropy. We consider a environment measure. So in some sense, this identity generalizes this well-known variational principle. So what is my motivation? Because many natural measures appear in dynamic systems, especially in smooth dynamic systems. It's not necessarily environment. For example, you consider the basic measure or consider some natural measure of the smooth method. But because it is not environment, so in this sense, the classical entropy theory cannot work well for such statement. So, but we still want to study in some sense the osmotic behavior of the dynamic system. So it's an instance is natural to study the need of some non-invariant measures. But for example, for this natural measure. So in essence, one possible way is to examine those up and lower measure entropy, so that we can know something, because this entropy its definition is also involved the object of the system. So maybe we can know more about this. So then the question come to me and feel is that if we consider the identity proved by Feng and Huang, can we discuss the for some analytic seed? So when the subject has or has no measure of matter entity, what do you mean measure of matter entity? That means this. So can you given analytic seed in a topological dynamic system X, can you find some measures with support on Z, but is measure-theoretic entity attains the corresponding topological entity. So that means the forward topological entity equal to its lower measure-theoretic entity, and the pattern topological entity equal to this. So we want to say is it possible to state the condition for this state. And also for obviously this depends on the system. So also for the system. So this is our setting. Because the corresponding question for the classical variation principle has attracted attention of many researchers. So here I only give a very short list of each. So and then by this question, so there are several different topics are around it. For example, people are interested to discuss the environment measure of matter entropy. So one typical way for this is to try to consider whether the function of the measure-theoretic entropy is absolutely continuous over the imaginary measure, that is USC. So once this, but this only can only tell us if there exists, but we don't know how many such imaginary measures. And there's another typical such measure is called the gypsy measures. Okay, so for each of these, there are many results about this. So we think probably if we consider such things for measures, maybe not environment, we can even obtain some interesting information for it. So now let me turn to the Goodman's question. So let me give the definition of the Borel topological entropy and the pattern topological entropy. So in fact, the Borel topological entropy is introduced by Leighton Borel around more than 50 years before. I think the definition is inspired by that of positive dimension. So that means we try to cover the steady state with some Borel board, but the Borel board here and with the different states. If we use the same state, is in fact the usual cover entropy. We will say a little about it in next two slides. But if we consider the different states of the Borel state, then we consider the infinite of turning over of this. Then we will obtain some quantity. Then if we let this n tends to infinity. So this you will find this quantity behaves very like in the definition of the homological dimension. That means there's a critical value x such that this value will jump from 0 to infinity. So that means there's only one x such that this value may be not 0 and not infinity, but for all other such value is either it be 0, either it be infinity. So there's a critical value of some jump. So we will denote this value by this, and then if we take this parameter epsilon tend to 0, we will obtain some quantity. So we call this the Borel topological entropy. For short, we just say the Borel entropy. So then this is the definition of Borel entropy. So in fact, the definition of pattern entropy, there's only one small difference between. So that is this. So isn't all the other things. The only difference here is we take the countable paragraph running the family of this. Here we use the closed word, but it doesn't affect too much. So, but here we consider the parent running. So how to say each has it goes back to the definition of the pattern dimension in fractal geometry. So this is why it's called the pattern dimension. So it also has some good properties. So as I mentioned, the topological entropy of a substrate. So this is the topological entropy of substrate. I mean the cover topological entropy. So but here I use the spanning because how to say in our paper in order to manage some for technical reason we use the spanning set. So I give it here. So that means given a substrate, given a step n, given a parameter epsilon, we can reduce the what we call spanning, nf spanning, and then we can consider the minimal to the negative of a C spans the frequency state, and then we can use this as the usual topological entity or the cover entity of the substrate. If we consider the third phase, the third split phase, then this is the usual topological entity of the system. So the trivial point of these three the definition is there is some relationship for each. So for example, with this we know that for example we know in general for topological dynamic system, if we consider the cover entropy, a countable set can have a positive entropy, but in some sense it's not so good. Okay. The set can have a positive, can have only have a countable point, but it's a topological entity big. So, but for this to entity is even better. If the point is a countable set, then it's by this fact, it's easy to say that if this kind of entity is also there. So the good relationship between these three entities is that if we are interested in a dynamic system, then the whole space has the same three entities. So that means you consider a compact invariant subset of the system. These three entities are the same. So all of them are easy to obtain, but it will be very helpful for us to understand them, and also it will plays important role in some analysis. This
You just remind what the conditions on the Z, how large it is, to make sure that the last line
is this that compact an environment. That means the substance of this.
but I mean, to make sure that it's not, say, 1 point fixed by or something like that.
Sorry? You mean?
No, but with respect to Z, the equality is.
Ah, I see, I see.
It's not
It's not any for not any for
I mean, how do they see inequality? Can you say something when there is equality?
sorry.
So let's say I cover with a countable,
Yes,
and I want a condition that I know that the supernorm attains.
yes,
I want an equality. Equality.
yes.
Is there such a good condition?
You mean, sorry, you mean for which?
So then no, one more.
Yes,
This,
yes.
I would like a equal sometime.
Oh, yeah. You are right. You will argue something. In fact, in our argument, some place, I think this wasn't easy for us to know. In fact, people using another formula. We use that equal so they equal to the zoom this way. Then this equal to yeah. That is equivalent formula. Yeah. You know some in some place we found we just something for that when you do it made it easier better for us. Yeah. So before going more detail about our results, let us give a summary of it. So that means we found that such kind of measures with maximum entropy is completely different from the if we consider the invariant measure of maximum entropy for dynamic system. What means completely different? The first one we could prove that there exists smooth system and a smooth curve such that you're supposed to know any measures of maximum entropy. Because we know that in a smooth dynamic system, there always exists invariant measure of maximum entropy. So this is the first difference. And the second difference is we know that in many systems, or there is no measures of maximum entropy. But here we found, in fact, in any given possible entropy system, there always is not typical analysis. So what is typical two types of analysis state? That means it always there exists one analysis state that either admits maximum entropy measures, and there always exists another class of analysis state such that it admits no measure of maximum entropy. No matter consider the formal entity or consider the packet entity. In fact, the main argument for these two types are completely the same. And then the third is because we know that this shows that the difference of each from the zero case. Then people may be interested. Can we say something? Can we give some conditions to see? Okay, for this case, we know it admits measure of maximum entropy. For other, we know. So our first point about this, but we have to add some conditional with further edge cancel system. So the better thing is in our arguments for technical reasons we have to use some expression from this thing. We don't know how to weighten it. We try to weighten it more than 1 year, but we say that we can only for every transit system. We did can verify fully the conditions for it. And we will give the more detailed about it by introducing the new concept for the increasing countable entropy slides. So now let me move to detail about our result.
May I ask you a question?
Yes.
Because I'm trying to see how to use your result. So let's say we have a manifold.
Yes.
And we have an attractor, and we know, for example, that the Lebesgue measure
Yes.
is physical.
Yes. Yes. True.
So, and if we can calculate something with respect to subsets of it, can we now say something about any limit point of the iterations or the averages of the iterations? So I can transfer some information from the measure which is not invariant to any limit, so in particular to the good limit.
To be honest, now I'm not sure. Yeah, I'm not sure. In some sense, at least now I have no good idea to produce such information. But probably we can do it in the future. But now I have no good idea for this. Okay. So now let's move to the more detail about this. So we know that the high smoothness of the map over a smooth system is very important in the study of to ensure the existence of environment measures with the maximum. We know that Katok has a famous result shows that a smooth map over smooth manifold has a measure of maximum entropy. In fact, the way they do it is try to prove the function in the USA. And in this century, the Boozy showed in fact we cannot wait this event to CR for any. In fact, something many years ago, the Polish mathematician Professor Michel, he also gives some example, but he only for some special, not for each part. And then, in fact, the smoothness of the map and also smoothness of the manifold also will help to you want to estimate how many such environment. We know if you want to know how many such environment of maximum entropy, so it's important to know how many orthogonal environment with maximum entropy. So then Sarah will prove or famous that for some cases we can prove that okay, at least we know that there are at most countably many orthogonal environment with maximum entropy. And later they can in some result. That means in some cases they can know that there are only many orthogonal environment with maximum entropy. In fact, some can know only one. And there are also many other such results. Because I'm not working in this region, so I only know a little about it. So this is
we had a master class by Brin in the Simon semester about this result.
So
we had a master class in the Simon semester given by Brin.
Oh,
where he gave the full proof of the result.
Okay, good. Okay.
So we know it's not
There's the recording.
there is a so if somebody can remember the context now.
Okay. Thank you for your clarity about this. Yeah. So we found that the smooth structure will not give up. In fact, we can construct such an example. We found that there is a three-dimensional map over the square, such that the smooth submember, in fact, is the diagonal of this square, such that it omits no maximal Borel entropy, and it also or there is no measure of maximal cutting energy. So we have said that the construction on the other hand, for this type of energy, most places are completely the same. So therefore, sometimes I just said about the Borel entity. So in fact, our idea is very simple. We just to construct a three-dimensional map of a square such that we can partition the diagonal into a common union of these, and such that each part delta I has a strictly small entity. So what means that means just this data I is the first. This is not partition, but you can also do this. This is not, this is the increasing union. But this is the same. If we change that into the same. I mean, this we continue this, and then how to say it? Our construction is in fact, if we consider each such lab, in fact, is a subsystem for us. And from this, we know that this part will be a subsystem. So we want to buy some construction so that we can know some construction, know some control of the entry of this type, so that we can control the entry of the data I. And we can also by some way using the something from the one-dimensional dynamic system, so that we can control the entry of the third directly. So that means later we will first try to such that the entry of this will be strictly smaller than log 2. This is finished by because we can see the G segment is a subsystem. We need only control the entry of this segment. We can finish this, and so because this is the substate of this, so we know this, and then we will using some feature from the one-dimensional system. We can do this. That means the forward entry and the packet entry of the third diagonal will have entry log 2. So also we want to make it will be a smooth map. We also use some degree from the one-dimensional system. So that means in fact we use such kind of pre-forecast so that if you want to control the entity, we want to in some sense we are interested some good parameter of the AX. So that means we want in some cases the map is locally dimensional on two, so that we can control the entropy of the whole diagonal. And we also need the AX to be smooth, so that the control map is also smooth. And we want to we want to have a good control over each segment, for any over each segment. So we also need sometimes the such parameter is locally constant in some small short interval.
But these two parameters, you mean that A is a function of some parameter?
Yeah, the function of the X.
So what are these for some parameters? To which parameter are you referring?
AX, parameter, I mean AX.
So AX is a family of functions and you are choosing.
Not the family function, just a function.
But it depends on some parameter.
No, depends on X. Oh, so here I mean parameter doesn't mean AX.
X is the parameter.
Yeah, oh, I mean parameter, I mean AX. So it depends on X. So depends on X, that means for you know, X is depend on 0 to 1. So I maybe require in some short segment of X, we want to X is another company, but not always. But we also want to say X is is smooth.
So it's infinity, but just constant on some.
Yeah. But how to say, you know, the idea is this. But there's one thing we need to check why this is enough to say this diagonal will satisfy the condition. Because that means how to prove this diagonal has no measure of maximal entropy. So in fact, the idea is coming from the following fact. So that means we can prove that if you can rewrite the analysis as a union of countable analysis C, and each NZI has strictest more entry, then we can prove that once a measure satisfied is supported on this Z, then the measure NP will be strictest more than the Borel NP. So that means each measure will not be a measure of maximum entry. So in some sense, they have no measure of maximum entry. So how to prove it? This is the fact for the following lemma. Lemma in fact is so important is very easy, but it plays an important role in this table. Why? Because we follow this table lemma on the fact. So we give a certain condition such that it already is no invariant measure. But then we found by many cases we can prove that in fact this is also a meaningful condition. So the lemma is that the lemma tries to tell us some information about the local measure entropy. So that means if a measure has maximum entropy, then we can see what happens with the local measure. So we found that if the local measure is equal to the Borel measure, Borel entropy for almost every point. So once we can prove this, then we know that by the definition, it's easy to say that for any something with positive measure, then you have the same Borel entropy. So then, if they can be represented as the union of countable states. So once a measure is supported, then it is. If measure mu is supported on this, then we should know that one Zi should have a positive measure. At least one. But with that level, we know that that part should have the same Borel entropy with Z. So it's impossible. So again, the problem with this is in some sense it's just a greater analysis.
Sorry, the same lemma holds for the packing entropy in the upper.
Yeah, sure. Yeah. So the estimation is just to say you want to prove that we want to say how many points is low entropy is bigger than Borel entropy. How many points is entropy is low entropy is smaller than that one. Because we know that it's integer is just this. So in fact, we want to prove that for the point bigger than that one, zero entropy. There is sorry, zero measure. The zero measure. There is none. So okay, we assume it doesn't hold. We can consider that it's a normalized measure of mu restricted over this positive measure 6. Yeah. So then it's easy to say that by the variational principle proved by Feng and Huang, we know that this should be smaller than zero because their variational principle says that the Borel entropy bounds the measure entropy. But from our construction, we know that each point has entropy strictly bigger than that one. So this one will be also bigger than one. So that means this correct or contradiction. So we have shown that this is different than the usual case. That means the smooth curve, the smooth system. Sorry, so the smooth curve system. The smooth curve system may have no measure of magnitude. So we want to
you show now the first point, but the second point now is open in the lemma with no one previous. Yes, can you explain this? Why?
Because you know, you how to say first, because it's a subset of this, yes. So if the energy is more than this, yes, then you will know that the mu is transportable measure of k, yes. Then we consider the normalized measure mu of k. This will be a measure sort of k, yes. Then we can use this mu can calculate is normalized. The number entry is normalized one. We know that for even not only for the mu but also for the normalized measure, if lower entry is also this. Then by considering integer, the lower entropy of this normalized measure entry also this. So then we know that the entropy is this. Okay.
Yes.
Okay. So now we will show that very easy from system. Even the system is very good, and also we know that there's some a very good substrate in a system, such that you have no some barrier. So you maybe how to say we may expect maybe we can find some system such that probably all of these analysis have measures of maximum energy. Because we found this very good, but maybe we can add some more conditions of the system, more assumption of the map. Maybe all analysis will be good, but we found there will not happen. In fact, we can prove that there are two typical analysis states in each system. So that means we can prove that for any given system, if you have positive energy, then we can construct a subset, such that the subset, these two have the same value, but and positive, but it always has measure of maximal packing entropy and also maximal forward entropy. And we can how in fact we can relate the entropy of this state will be arbitrarily close to the entropy of the whole system. Why we can do this? Because okay, let me talk later. Next, let me also further explain this point. So we can also prove that we can find another typical substrate such that they two also have the same energy, and it has no measure of maximum energy. In fact, this case is much better. Here we can only say that it will be close to it. But here we can deal it for each given possible value between 0 and the system. So now let me move to why this.
Sorry, I have a question.
Yes.
So in first point you say that no, sorry, in the second point, there's no measures of maximal packing or Borel topological entropy.
Yeah.
By this you mean that both?
Yeah, both. Yeah. Sorry, not my English. I'm very sorry for this. Yeah. So first, how to do it? First, because we need to say when the measure in something good measure. So because we are interested in lower entropy and upper entropy, so we want to analyze the local entropy. So first, we want to say, oh, local entropy, that there are something about it forward entropy and is packing entropy. So we found that in fact this result how to say it. In fact this result has may go back to practical geometry. We prove use some idea from that. And then so our proof of the first atom is because we use the Brin family result. That means they can show that for the according to environment measure, the local entropy not only the lower but also the upper are both equal to the usual mirror entropy. And then we know that by the variable principle, we know that the measure of algorithm, the entropy of algorithm invariant measure may be close enough to the topological entropy. So if we consider the generic points of the algorithm measure, then we will provide the first item. And then in order to prove another result, we need to use another result proved by me and Huang and Zhang the transaction. So we could prove that for any in some of this paper we try to discuss whether we could lower topological entropy of subsets. I mean, of subsets. So that means we finally proved it is possible to lower entropy of subsets. That means for any given such a H, and there always this some complexity such that their entropy are both equal to this H. So with this, by some analysis, we could prove that this stage very satisfies the condition for signal atom. So now let's move to the third part of third item of our result. So we try to give some good characterizations of analysis in every quantum system. So what is every quantum system? In fact, this is a very important class in smooth dynamic systems. Its definition is given like this. It is using the topological entropy of some we call the stable states of the local stable states. So it's definition is this. So in fact, we can work for the quantum system by using the increasing countable entropy slider. So what means the countable entropy slider? So let us move our result will be, and then we see what is this. So in fact, our result is stated like this. So that means the original sufficient condition is in fact sufficient condition. So that means a state has no measure of maximal entropy, even and only if you could write this Z as a union of countable states Zi, such that each Zi has entropy strictly smaller than this one. So because we think this shows that this state can be rewrite as a increasing union of countable slides, and each has entropy small, strictly smaller than the first state. So we call it the increasing countable entropy slides. And for the packing entropy, we have a similar characterization. In fact, for global entropy, we can give more characterizations using the language of the gauge function, GAUG gauge function. Because one, okay, I will not talk about that, but I forgot the name of that person. That is something I can say more something about this characterization. Okay, I want to give an application of our this characterization. That means with the table of this class, we could have following coming for analysis with possible dimension. So that means if given analysis with positive dimension, then we know that either the C has no measure for lower dimension, or in some sense you can also rewrite this Z as a countable slide of increasing something, increasing possible dimension. That means so what means the measure of 4 lower dimension. So if given like this, we have said the formal entropy is defined similar to possible dimension. So I will exclude this one. So then given a measure, we can also reduce the function to the possible dimension to measure this possible dimension measure. So then what we means the same state. This state has a measure of 4 lower possible dimensions. So that means the measure such that the measure of the lower possible dimension of this measure has the same with this state. Then we will call this state has a measure of 4 lower possible dimensions. So then with this, how we apply our result to then this application is we want to study this system. The system is given is like this. So it's easy to say it's a passive dependent system. And is by direct calculation, we know that there's some relationship between this forward entity and its total dimension. And then the fourth thing is we can give direct relationship between the local entity and another quantity d mu x. D mu x is the definition given W. But why this is very important for us? Because according to the well-known result from Frank geometry, we know that the lower total dimension of measure can be given by this quantity. So that we can apply our result to about the measures of maximum Borel entropy to like this. That is the measure of 4 lower possible dimensions. So I just want to give very small question around this, or at least this is something.
Slide. This was the code that you showed for about house of dimension.
Yes.
That this is a new result that you prove by analogy of.
To be honest, I didn't find this result in the literature.
Okay. And what is now the role of the slide about what you did with the H?
Yeah.
Yes. What are you trying to say? What is this slide?
I mean, how to apply our result to that curve?
Oh, so this is how you prove the.
Yeah, how I prove this? Because there's no dynamic system here. Only the total dimension. But our result is about the dynamic system. So I want to tell you how to apply our result to prove this. Yeah. So this is a small question for us. How to, at least we don't know how to solve it, but maybe it's maybe not included. I'm not sure. So that means to try to say something for analysis, such that it provides some good. I mean, to provide some subject condition. I mean, something not that kind of characterization. I mean, something so invariant what content. I'm not sure it's very good. And also, we have said, I have said that we try to weaken the condition of every sample for around 1 year, but we failed. So we don't know if it is possible. So I think I should stop here. So thank you very much for all of your attention. Thank you.
Thank you. Are there any questions? Yes.
Yeah, could you go back to the result of the existence of the Borel sets for which the variational principle does not hold?
Does not hold?
Yeah.
In this one or in the next one?
I think the previous one.
This is the first one. But here, before is our example.
The example. Okay, so then further. Okay, so my question is just
yes.
This. So you prove that there exists Borel sets for which the variational principles. The measure of maximal entropy.
Yeah, or no measure of maximal entropy.
Yeah. And now, if instead I ask you about the equality between the packing entropy and the Borel entropy, can you prove something similar, that there are sets that you can always find a set for which they do not coincide, or is it?
Yeah, it's very easy to find many subsets such that these two entities are different. Yeah, it's very,
It's easy to construct.
yeah, it's very,
Okay.
yeah, it's no.
Okay.
It's
Okay.
no.
Thank you.
Yeah. Yes.
Good question.
Yes, please.
First of all, you did this factorization for H expansion.
Yes.
So it's very natural to ask about asymptotic.
Yeah, I try to do it
That's
fair.
the next.
Yeah. So we try to do it a single around 1 year. With Shule.
Only for the asymptotic.
Yeah, only fair. Only fair. You know, I think it's no matter. Because for topological, study of topological dynamic system, sometimes once you could prove for every capacity system, in general, you can also prove it for every capacity. When I'm sure it's natural, but we try to.
Okay, and on the other side, you said that you show that for positive entropy, you show the counterexamples, but if you now consider CPE or UPE, so what I mean is, complete positive entropy.
To be honest, I didn't consider, but even CPE, UPE, that means there is two kind of structure. Yeah, for any for any. Yeah, for any. But I don't know whether some others. I mean, I didn't to study this to have two kind of system to say you will connect to more about it. I don't know. But that is that for any.
Okay, so
Yeah. Even how to say one possible direction is to consider this is maybe we don't consider consider general subset, not only analytic set. In fact, there's also that means we know that for analytic set there is variational principle. If we consider general subset, what will happen? In fact, there's also was done by me and Shule, but I'm not willing to here. We did something for that.
Okay, another question? If not, let's thank Guohua.
Thank you very much. Thank you. Thank you for everything. Thank you.
When is the next one?
Well, maybe.
Great.
Yeah, we can.